Hello everyone, my name is Lukman Said, and in this short lecture, I will talk about the ordinary least square method, which we can use for estimating the unknown parameters in a linear regression model. Well, imagine that we want to study the relationship between years of schooling and earned salary. Well, we believe that years of schooling has some effect on the earned salary, and luckily we have some data on both these variables, where years of schooling represents the number of years the person attended the school. And then we have the corresponding data on the earned salary, which is measured in thousands of pounds. So as a first step uh, towards examining the relationship between these two variables, so we plot them together, and with years of schooling on the x-axis and earned salary on the y-axis, it appears that both variables are positively correlated because the boat appears to move in tandem. So as the years of schooling goes up, it appears that there's a corresponding increase in the earned salary as well. However, to better summarize this data, what we can also do is to draw a line over these data points, which we formally refer to as a regression line. And because it is a straight line, so we can mathematically represent it by the equation for a linear line, which is y equal to mx plus b, where y is the earned salary and x is years of schooling, and m represents the slope of this regression line, and it simply measures the effect of the change in the years of schooling on the earned salary. So for instance, if m is equal to zero point 0.6, then it means that if the years of schooling goes up by 1 year, then the earned salary goes up by 0.6 thousand pounds, which is 600 pounds. B represents, we will call B as the intercept of the regression line, and for now we can remember that B represents the value of the earned salary if the years of schooling is 0. So if somebody has no schooling, then B would capture the earned salary for that particular individual. Now, remember that this line was arbitrarily drawn. So I just drew this line, and so how do we know that it best fits the data? So how do we figure out what is the best fit line? Now, for instance, if we have another line, so let's say we have a blue dashed line like this. So how does it compare with the red line? Does this blue line better summarize the data? Or for that matter, if we have another line, let's say a green dashed line like this. So to figure out like which is the best fitted line, that's where the ordinary least square method comes in. So it's the ordinary least square method. So let's refer to it as the OLS. So the OLS actually helps us to identify the best fitted line, which best represents or best summarizes the data. Now, according to the OLS method, the best fitted line is the one which has the minimum error, which bears the question that what are the errors? So the errors are simply the difference between the actual and the predicted value for y variable. So for instance, at 12 years of schooling, the actual value for earned income is 27,000 pounds. But the predicted value or the fitted value, which lies on the regression line, is 25,000 pounds. So we could say that the error is actually equivalent to the difference of 2,000 pounds. So that's the part of the actual earned salary, which correspond to 12 years of schooling, which the regression line fails to predict. So that's why we refer to it as the error. So likewise, we have errors which which correspond to the other data points as well. And of course, we can quantify them because the errors are simply the difference between the actual and the predicted values for y variable which lie on the regression line. So, as I said earlier, that according to the OLS method, the best fitted line is the one with the minimum of errors. So, if we have another regression line, then we can compare the errors from this blue line and the red line, and we consider the best fit, which has the minimum of errors. But then the question is that how do we compare the errors? Well, ideally, we would like to sum all the errors. So we sum all the errors, but since we have both the positive and the negative errors, so if you sum them up, so it is possible that the sum comes out to be equivalent to 0. So the negative and the positive numbers, they just cancel each other out, just like what happens here. So to avoid this possibility, what we do is that we scare the errors and then add them up, which we then refer to as the sum of the squared errors because the errors have been squared. Okay, so then between the different regression lines, we compare the sum of the squared errors, and the regression line with with the minimum of the errors is then is our best fitted line. But does that mean that we have to find the sum of the squared errors for all the possible lines which pass through these data points? Well, no, because the OLS method actually does that for us. Because remember that a regression line, a linear regression line, can be represented by the equation y equal to mx plus b. And y is the dependent variable and x is the independent variable, and m and b are the unknown parameters that we have to solve. Now, the OLS method, helps us to identify the solutions for m and b, which actually minimizes the errors. So we do not have to compute the errors for all the possible regression lines which pass through these data points. Rather, we simply apply the OLS method, and we will discuss that in our next lecture. How do we do that? And then, the OLS method provides us the solutions for M and B for the regression line, which actually minimizes the errors. So to sum it up, OLS sets the criteria for the best fit line, and the criteria is that the best fit line is the one with the minimum of errors, and it computes the solutions for M and B, which are the part of the equation, which represents the regression line. It yields the solution for M and B, which actually leads to the minimization of the errors. So this brings us to the end of this lecture, and I'll be happy to take any question.